We're beginning something new today because what we've done up till now, very early part of this course, we dealt with members that were going to be loaded axially down the length. So we called those two-force members, and we had certain formulas that we could deal with that. To find the stress, we would just take force over area, but we also came up with a formula that allowed us to figure out how much those members would elongate or compress under certain loads. So that was sort of the first part of what we did, and then we moved from there to members that instead of being pushed or pulled like this, members that were flexed like this, and we called that flexural stress, or we would call that like beam deflection if we looked at how far it would actually move under those kinds of loads. So most different kind of loading that happens out there in the real world is kind of typically a combination of those first two that I just talked about, axial, flexural, and then what we're going to start talking about today, and that is torsional, right? So with axial, you're either trying to elongate or compress probably a long, slender member along its long axis, right? Kind of that way. With flexural, you're pushing on it to see if you can, how much it will hold. Basically trying to deform the location of that long, slender axis. And then today what we're adding is the possibility that we could try to twist the member around that long, slender axis of our members, okay? And this type of loading is called torsion, all right? And so our first article of business that we have to do here is to come up with an equation or a formula that will allow us to find the stresses that are induced in a member like this when you begin to twist on it in this way, okay? So by way of introduction to this, let's start by looking at the left body that I have drawn up here on the screen. And ultimately what I'm going to try to do is use things that I know about how that body will move under this twisting action, that torque, right? That's what my T value is right there. Under that torque, what this thing is likely to do, okay? So what you can kind of look at there is that I've got this long line drawn along the edge of this member. So here it is in real life. You see that there's this line that's drawn down the length of this member, and before any loads are applied, it's just applied to the side of this member so that it just goes straight along its side, okay? And then, as we apply this torque to it, what happens to that line? Okay? If you're going to be real technical there, you'd probably say it looks like it starts to become kind of helical, right? It's sort of this twisty type of shape to it, a helical shape, okay? Well, let's look at that on this member and actually see if we can draw that and identify a couple of parameters here. So first of all, let me draw a line. Actually, I meant to put that in blue here. Let me draw a line that shows how much we have actually twisted this member, right? So we're twisting it, and I'm going to call that amount that we've twisted it theta. Okay, theta, we're going to actually get into that a little bit more when we meet next time, but this is called the angle of twist. We're not super creative, but that's what it's called, the angle of twist that has been applied to this member as a result of this torque being applied. Well, if that's how far the kind of the end of the thing has twisted, then what would happen to that line that I have drawn on the edge? Where is its new location? Okay, without getting too, complicated here, what we'll do is we'll just imagine that this end, since it's attached to the wall, is going to stay there, and it's going to stretch out, and there's going to be the new location of that line as a result of this thing twisting. Okay? And this is the starting point for us to understand what's going on in a twisting member like this. So let me start, again, still on the left side over there. How far does that point right there move with respect to the dimensions that are shown there? Well, one of them that's easy for me to identify is that that point will have lifted by about theta times c if theta is measured in radians. Would you agree with that? especially if that angle doesn't get super large. As a matter of fact, maybe I've drawn it more than I really want to draw it there, but I want you to be able to see it, so I put it there probably larger than a normal angle of twist might be. But, you know, let's say that if we have that theta measured in radians and we have a radius of c, then that means that that point will have moved by approximately a height, and I'm going to just kind of draw this on here in a not real technical way, but let me say that's a height of h1. I'm going to say h1 is equal to theta times c, as long as c is measured, or c is a radius and theta is measured in radians, right? And that's approximate, but it's good enough. Well, another way that we can look at that point and how far it moves is by looking at an angle over on this end, right? Along with length L. Now this is where this gets very, very interesting, because that angle over there on that end is something that we actually can relate back to in some way. And let me show you why. On this little piece that I've got in my hands here, you'll notice that if I twist it, what happens to the shape of that piece that starts out being rectangular? It becomes a parallelogram. Have we seen another stress element where that's what it did? Okay? Strain, and specifically shearing strain, you might remember, and I'll draw this a little bit funny probably here, but let's say that we start off with an element. I'll draw it here. Tell you what, I'll draw a little element like this. Okay? And if it's in a set of coordinates like this, and let's say I've got this end fixed, and then I put a shearing stress over here on this side, what we've seen already is that this member is going to become kind of parallelogram in shape, like this. And when we did this, where did we identify the shearing strain for that element? What dimension would I identify here for the shearing strain in that element? Right? It was how far did this thing angularly distort, right? We had that gamma that we would identify right there. Okay? Back to our specific example that we're working with here. Where would that gamma be if that's what we've got going on the left figure over there? Wouldn't that just be this angle right here? Yeah. So let me do this. Let me, instead of just calling it gamma, I'm also going to put a subscript on it. I'm going to call this gamma sub c, because this is happening at a radius value of c, right? It's happening out on the outer surface of this member, which is at a radius value of c. And based on this, and also assuming that gamma sub c is in radians, we can say that this h value that I've got right there is also going to be equal to gamma sub c times L. Okay? And then I want to rearrange this just slightly. I'm going to take this same expression and rearrange it so that I solve it for theta over L. If I solve this for theta over L, what does this end up being? Gamma sub c over c. Okay? Good. That's actually the first thing that I wanted us to look at was, you know, the relationship that happens between the angle of twist and the shearing strain that is induced on the outer surface of the member. That's what we just figured out, is that relationship between our angle of twist and that shearing strain. Well, the next piece is a little bit stranger, right? This member that I showed on the left is a solid piece of material with a circular cross-section, right? What I want you to do is imagine taking a core out of the middle of that cross-section and imagine what kind of a shearing strain is happening on that little core. Okay, so that's what the picture on the right is. I'm trying to get you to see with the light gray line there. That was our original member, but I want us to not think about the outer surface of this member, but rather some little piece of material on a you know, like a cylindrical piece that's going through the middle of that member, right? This piece I've got right here is hollow. So one way of looking at this is this would be, you know, imagine if this wasn't hollow, but imagine that same shape. I'm trying to take out a core that looks like that, and I'm going to do that at a radius of rho. And I'm going to draw this letter a lot. Don't confuse it with p. It is intended to be a parameter that indicates a radius. Okay? So there's that, and if we think about the original picture, I had this line that was going from the middle point, right, up to, let's see, try to make it somewhat similar here, right? It basically went up to here or so. All right, but I don't care about that so much because what I want to do is look at what happens at this point right here, and what does that imply as far as the strain that's going to happen on this interior little piece, right? Something like that, okay? I'm going to give this one another letter, right? I'm going to call this one gamma sub rho. Actually, let me draw that in a little different spot there, okay? We'll say this little angle right here is gamma sub rho. It is still a length of L, right? So if we do something similar to what we did in our first case, only this time we're trying to figure out how far does this point move this point instead of the one that's out on the outer surface of the piece, right? What we'll say there is say that's H2, right? That's going to end up being, this is still theta, right? So this is going to say that theta times rho is going to be equal to gamma sub rho times L. All right? And can I solve this for theta over L? Because theta and L are not different on the second case versus the first case, right? Theta and L are the same theta and the same L as I had in my first case. All I'm doing here is I'm looking at some other little piece of material that's inside of my original piece of material, and I'm coming up with what's my shearing strain at that location as opposed to the outer surface. Okay? All right, so this just means that this is equal to gamma sub rho over rho. You might go, okay, fine. So what? Well, let's actually take these two, and because they're both set equal to theta over L, why don't I take both of them and set them equal to each other? Gamma sub C over C is equal to gamma sub rho over rho. Okay, and I'm going to change this up just a little bit. The first thing I'm going to note is I didn't pick any particular value of rho. I'm going to let rho be a variable that will describe any cylinder of material inside of the bigger cylinder. In other words, rho can vary from 0 to what? To C, and that by changing rho, it picks a different cylinder inside of my main cylinder. And because of that, instead of calling it gamma sub rho, let me call it gamma as a function of rho. Right? It's valid, right? Because it can be true for any rho that I'm talking about, any radius that I'm talking about. And let me solve it for that and put everything else on the other side of the expression. So what that means on the other side is that I'm going to have gamma sub C. Now, let me also think about maybe a different notation for gamma sub C. Is there any other material in this part that has a larger shearing strain than on the outer surface? Okay. So I'll draw it, I'll write it like this at first, gamma sub C, and then this is times rho over C. And rho can vary from 0 to C. So what's my maximum gamma? Where does it occur? A rho value of C, right? Which means that gamma sub C, which is the shearing strain that happens at a radius value of C, I can, instead of calling it gamma sub C, it would not be wrong for me to think of this as a gamma max. Does that seem like an appropriate thing to name that value, since there's not another location in the piece that has more shearing strain? Okay? Well, the next step I want to do is, let's assume elastic deformation. If I assume elastic deformation, what you can do is think back to our stress-strain curve, and you might remember that one of our stress-strain curves that we looked at involved shearing strain and shearing stress, right? And there was, for this curve, a linear portion here in the middle, or at the beginning, I should say. And what was the relationship there in the linear portion? One of the ways that you can express it is that stress was equal to modulus of rigidity times strain. So if we assume elastic deformation here, then one of the things I can do is multiply left and right of this equation by modulus of rigidity, G, and that will give me a shearing stress on the left side, right? So basically I'm multiplying both sides by G. On the left side, what that gives me is shearing stress as, shearing stress as a function of rho. Right? On the right side, it gives me maximum shearing stress times rho over C. And that result all by itself is interesting to us, because what that allows us to do is understand that the stress distribution across the face of this part is going to be linearly distributed as you move away from the center axis of the piece. And if you wanted to sketch that, you could basically say that there's going to be a stress, right, that is sort of linearly distributed. And regardless of what line you look at, like in other words, I could draw a line, let's say, up like this. Whichever line I look at, the stress is going to be distributed, right, linearly as I move away from the center, right? So this is either of these values, or either of those like sketches that I put right there, would represent the shearing stress as a function of rho. And it varies linearly as we move away from the center. Okay? Well, so that's kind of interesting, but it doesn't really do for us what we probably need yet, because one of the parameters we haven't pulled in is how much torque we're applying. And your intuition, if nothing else, would tell you that the amount of torque that should be a parameter that matters, right? And we haven't pulled that in at all yet. So what we need to do now is imagine taking this this piece right here, and imagine making a cut, right, through the middle of this thing. Okay, I'm going to cut off the tip of this thing, and I'm going to look at the back side of it. Okay, so I'm going to make a cut like that, and I'm going to look at just this portion on this side. I'm going to do a little sketch of it down here. Okay. Looks something like this. And if I pull over the torque, now that I've flipped this around, that torque that was kind of drawn in that direction, to draw it properly, now that I've got it flipped around, I would draw it like this. Okay? And this is the cut that I just made. So what kind of stress happens on this face that I just made the cut? Well, shearing stress, obviously, right? Because that's what we've been talking about, is a shearing stress. And we're saying that that shearing stress is linearly distributed, right? Which means if I draw a line, say something like this, right? It's got to react against this torque. So the torque is trying to move this thing one direction. This stress, which is, again, linearly distributed, is reacting against it. Okay? So how can I make a relationship between the torque that's being applied there and the stress that's occurring on the face? Well, if you have a feeling that we need to do an integral, you probably have the right feeling. Okay? And the deal with integrals is we always want to take a little differential element so that within that element nothing is varying. Right? So we look at this, and our big variable here is rho. So we need to take a little differential element so that rho stays constant. Right? And the way that we think about that is to just basically make a little donut. Okay? Something like this on that face. What this allows us to do is have a little differential amount of area that is all at the same radius away from the center, right? I'll put that here as being a value of rho. It's all the same radius away from the center. Therefore, it all has the same stress, right? And if I take that stress and multiply by the amount of area that I have there, which, by the way, the reason it's a differential amount of area is that it's infinitesimally thin. So we could call that like d rho. But the point is, this ends up being what I would call dA. Okay? And what happens if I multiply dA times tau as a function of rho? What is stress times area? Force, right? Force over area gives you stress. So stress times area gives you force. And if you think about how this force actually acts, it's going to act kind of everywhere you look in this donut. It's always going to be acting tangentially, right? So it's almost like this distributed force in this, but it's always going to be acting tangentially to where the donut exists. And I'm going to call that distributed force right there dF. So I'm going to say here that dF is equal to that stress function, tau as a function of rho, times dA. All right? What happens if I multiply both sides of this expression by rho? What do I get on the left? Okay. I'm going to call what I have on the left then, if I multiply both sides by rho, like this. Okay. What I have on the left is the amount of torque that this little donut is contributing toward my overall torque. Okay. So this would be like a dt. And over here, let me pull that rho to the other side. I've got rho times tau as a function of rho times dA. Okay? Furthermore, I can do better in terms of my tau as a function of rho. I can substitute that in to my equation here, and what it ends up giving me here is rho times tau max, right, times rho over c. Now, what do you think I'm planning on doing with it? Okay, the whole point of setting up my differentials here is so that I can integrate them. So if I integrate the left end and say I'm going to integrate over the entire area and integrate kind of everything here, then what I end up with is that torque is going to be equal to, now tau max and C, those are constants, right? So I can take those out, and I can integrate over the area of the face of rho squared dA. All right. Now this is interesting. This value right here is another one that shows up fairly frequently in engineering. This mathematical construction, and therefore it gets a name. We call this thing a polar second moment of area. Okay? And you might notice its similarity in form to the one that we looked at before with beams called the second moment of area. What's the difference between that one and this one? Yeah, this one is essentially in a polar coordinate system because we are dealing with a radius value, right? That's what the rho value is right there. Instead of it being all these lengths measured to one axis in a Cartesian coordinate system, this one is more like a polar coordinate system, and so it's called the polar second moment of area. So anyway, this also gets a letter, J. Okay? And so if we replace that term right there with J and kind of solve it out, what we end up seeing is that our maximum stress is going to be equal to T times C over J. T is the torque applied to a torsionally loaded member. C is the outer radius of the member. And J is the polar second moment of area. All right? And this is an important equation that you're going to want to remember. Okay, now a quick question for you. What if I took this result and I plugged it back in, right, up here? Okay, the C's would cancel out, and what it ends up giving me is stress as a function of rho is going to be equal to what? T rho over J, right? So each of these is useful, right? They're actually kind of the same equation. They're doing similar things. The only difference is that tau max is the one at the outer surface, whereas tau as a function of rho is finding stresses at other locations, other radius values basically within the member that's being twisted. Yeah? J is our polar second moment of area. Yep. Yes, ma'am. That was what I was going to talk about next. We didn't say this much right at the very beginning, but all of what I just derived is technically only valid for circular cross sections. Okay? And the reason why is that circular cross sections are the only ones for which when you twist them, right, when I twist this, the shape of the outer surface of this thing remains cylindrical, right? If you try to twist something that does not start out being cylindrical, then a cross section that you cut through the middle of the piece is not only going to just twist, it's also going to warp. Okay? And that represents essentially more energy that you've got to put into the piece of material. It's going to end up causing there to be stresses that we wouldn't have predicted using a technique like this. So the only cross sections that what we've done here is technically valid for, right, you know, are the ones that are circular to begin with. Okay. Having said that, in some of your later courses, we're going to show you how to deal with members that might not be circular. But in this class, we're going to keep them all circular, and that'll help out a little bit. Yeah.
So is dA going to turn into rho, d rho, d theta, and all that good stuff?
So what I think what you're asking about is you might be saying, if all we've done here is just replace this integral with j, there's got to be another step here that we got to get to so that we can figure out what j really is based on the parameters that are associated with an actual cross section. All right? Which is exactly what I would like to do next. Okay? So for my polar second moment of area, I'm going to do this actually not for a solid circular cross section, because my other option I could do this for is a hollow circular cross section. And that's as complicated as this gets. So if I do it for a hollow one, then that basically covers all the possibilities. And if you think about this, you know, you can get a solid cross section just by making the radius value of the inner radius 0, right? So B on this figure right here, if you make that value 0, it represents a solid shaft as opposed to a hollow shaft. Okay? And what I want to do is come up with formulas for the polar second moment of area for this hollow member like this. So my first step is actually similar to what I've already done. I want to go out here and put on a little donut. And I want it to look good, so I'm going to use my little drawing tools here. Okay. So something like this, a little donut of material. And it's going to have a width, like I said before, of d rho, right? That's the little width of this little donut of material. We're going to say that it is located at a radius of rho. Right? And keep in mind that what we're trying to find here is j, where j is the integral over the area of rho squared dA. Okay? So really the main thing I've got to do is figure out what is dA, you know, relative to the kind of the size and shape of that donut. Okay? I'm going to show you a little trick that we can do to make understanding this a little bit easier. This is a super, super thin donut, right? Since it's super, super thin, I can still find the area of it instead of kind of thinking of the area of the outer circle minus the area of the inner circle or something like that. It's easier and more straightforward for me to imagine slicing it right in the middle and essentially unwrapping it. Right? Think of this like a little rectangle that has been wrapped in a circle around this piece and joined back together. Imagine like a little strip of paper that you've wrapped around and then taped in the middle and made a ring out of it. Well, let's take this and unwrap it. Right? If we do that, what it does is it gives us this long, skinny rectangle. And what are the dimensions of that long, skinny rectangle? D rho by what? The circumference. And the circumference is pi times the diameter, or 2 pi times the radius, which is the form that we've got, right? We've got rho, so 2 pi rho gives us the length of this piece. Okay? 2 pi rho is the length, d rho is the width, which means that dA is equal to 2 pi rho d rho. And I can plug that right into my formula for j, right? Which I'll do, and I'll pull out the 2 pi because it's a constant. 2 pi times the integral, okay, of rho d rho, and then I also got to get my rho squared that was already in there, right? So this gives me rho cubed d rho. And remember, every time you see this little denotation on these where it says this needs to be taken over the area, what that means is we don't want to tell you exactly what the limits might be for your area, right? But we're telling you to pick limits that cover the area. So now that we have our specific area here, let's pick our limits to cover the area. Yeah?
So we're not going to get a sector of a circle and have to do a double integral?
We don't need to take a sector and do a double integral or anything like that.
I meant like a all means class. It's not going to be
There are ways that you can do that, so I think some of you are eager to use some of your multidimensional calculus. We a lot of times figure out ways like this, like taking that little ring and unwrapping it like that gives us the same result without having to think in terms more of the multivariable.
Yeah, I saw that because 2 pi just takes that out, gives the whole circle. I just didn't know if we ever do like a quarter of a circle.
No, we don't do like a smaller segment of a circle. We won't need it. Okay? So what kind of limits do I want on here? Probably need to go from B to C. Right? B being the inner radius and C being the outer radius. And that covers the area. Those are the limits of rho that would use, kind of cover this entire area. Yeah? Yes, if we wanted to just do one for solid, we could replace B with 0. But if we do it with B, the resulting equation that we get can still be used where you plug in 0, right? Good question. So I need to take this antiderivative. How do I do that? Okay. Rho to the 4th over 4, and I'm going to evaluate this from B to C. So what that looks like is 2 pi times, C to the 4th over 4 minus B to the 4th over 4. And if I want, I can pull out that over 4 and combine it with the 2 that I have there, and this becomes pi over 2 times what? C to the 4th minus B to the 4th. Okay? And that is actually a formula that you should probably memorize. Right? J is equal to pi over 2 times C to the 4th, where C is the outer radius, minus B to the 4th, where B is the inner radius. Okay? He basically said he thought you were going to see this in the reference material. This is not one that shows up in the reference material. The reason why, we are only doing circular cross sections. So we will only ever have this as our way of calculating J. Okay? Now, there are a few little variations that are equivalent to this, but this is really the only one that you really need. Here's what I mean. What if I wanted to express this in terms of diameters? Okay? I could do this as, let's say, an outer diameter over 2 to the 4th minus an inner diameter over 2 to the 4th. What is 2 to the 4th? 16, which means this becomes pi over 32 once I combine it with the 2 that I already had in the denominator out there, multiplied by dO to the 4th minus di to the 4th. Okay? So, just keep in mind which ones of these are radiuses, radii, and which ones are diameters. But you should be able to handle your J without needing to look it up anywhere. All right. Shall we do an example problem? All right, we've got this shaft that is supported at its left end, so it's constrained from rotation at its left end. It has 3 different torques applied down its length. The segment between C and D is a solid segment with a radius value, outer radius of 7 millimeters. The segment between B and C is a hollow segment with an inner radius of 7 millimeters and an outer radius of 9 millimeters. And then the left end is a solid segment with an outer diameter of 16 millimeters. And the instructions say, draw a torque diagram for the shaft shown and find the maximum shearing stress carried in each segment. And then it says which segment is heaviest per unit of length and which is the lightest, assuming that the material has uniform properties everywhere that you look in the shaft. Okay? So let me actually, while you're kind of copying this down, a torque diagram is a diagram where you plot the amount of torque that's carried in any of the segments as a function of where you are located along the length. It's very similar to like a shear and bending moment diagram, or earlier than that, even when we looked at the deformation of axially loaded members, we would do a little diagram that showed how much force was in each segment. We can do that same idea for these torque type of problems, okay? And because I want to do this, you know, a little bit thoroughly, right? I want to kind of really show this. We can do this by making some free body diagrams, by making some cuts, right? Like I could cut through this member right here and do a little free body diagram right there and figure out how much torque was being carried in that little segment. Right? I've got 60 Newton meters. Okay? So what kind of torque would need to react against that 60 Newton meters in order to keep it in equilibrium? 60 Newton meters, but it has to go this way. Right? Okay? So if I'm going to do a little plot of what all of my torques are in all of my segments, anywhere between C and D, I'm going to be carrying 60 Newton meters. And if I'm looking at the torque reacting on a piece to the left, excuse me, to the right, torque reacting on the piece to the right, it's going to be going the direction of that 60 Newton meters. You want to define that as positive or negative? It's our choice. We get to decide what we're going to make positive or negative. We don't have a nice, clean sign convention in this type of a problem like we did for our beams. So what do you want to make positive? What's that? You want to make that one negative. Okay, we can make that one negative. It's fine with me. So what that means is, let's say this is 0 right here, right? And let each of these little squares, I guess, be 20 Newton meters. What that means is I'm starting out at negative 60, and it's going to remain at negative 60 until I reach my next transition. Okay? Minus 60. And then what happens between B and C? Okay? Kind of similar to what I did on the first one, except on this one, I'm going to make the cut over here, right? And with this one, I'm going to put 60 Newton meters on right here. I'm going to put 130 Newton meters on here. And what direction do I have to react in order to keep this thing in equilibrium? Probably that direction, but with what magnitude? Okay, you can mentally look at that and say that's going to have to be 70 Newton meters to react against the other two pieces. So this goes all the way up to 70, right, which is going to be somewhere in here or so. Okay? And I would just note that the difference here was how big? 130, right? So basically what we did right at the very beginning with that direction of torque of the 60 Newton meters, that made us drop by 60 Newton meters. And we moved from right to left, we then rose by 130 Newton meters to get to the level that we have in the segment from B to C. What do you think is going to happen with our next one? Okay, I'll kind of do it again like I did before, but draw this out. Something like this. And now we're making this cut over in the segment between A and B. Right? We'll have 60 Newton meters. We have 130 Newton meters. We have 40 Newton meters. Right? Which means that we have to react over here with how much? Okay? Yeah, 70 plus 40 gives us 110 Newton meters. Okay? So that would be approximately up here like this. And this is going to be our torque as a function of x, where this is x, right? And this is going to be measured in Newton meters. So that would be my torque diagram for this shaft. Now here's the thing. That was probably a little painful for some of you to watch because I took so much effort drawing each of the free body diagrams. And you're going, I get it, right? A better way maybe of saying this is that torque accumulates down the length of a shaft, right? Every time another torque is added, it accumulates in the overall torque that the shaft is carrying. And so what you have with each of the applied torques is basically a difference, right? So this is another 40 Newton meters difference right here, where this was a 130 Newton meter difference that happened in that first transition, right? Just like this was a difference of 60, or a negative 60 really. So anyway, does that make sense? So given all of that, what kind of a reaction is the wall applying? 110 Newton meters. As a matter of fact, for some of your problems that you might work on, it might not even show a wall or like a support like this. Instead, it might directly give you that there's some kind of a torque being applied just to that end, right? Now they can't just randomly, anyone who writes these problems can't just randomly pick all of the values, or else you might have a dynamics problem instead of a statics problem, right? If you end up not balancing all of the torques that are applied along the length of a shaft, it means that the shaft is going to want to accelerate angularly, right? So we're going to try to keep things as statics problems in this class, which means that whenever you inspect the problems that you work on, if it's got nothing but just applied torques like this, you should be able to go through and see how they all sum to zero. Okay? Even though in the real world there's no reason they have to sum to zero, it's just that if they don't, then your shaft will be accelerating. It won't be either stationary or turning at a constant speed. Okay? So there, I did my first piece of this problem. I figured out the torque diagram for this shaft. That makes the next part fairly simple. So the next part is to figure out the maximum shearing stress carried in each segment. Okay, which segment do you want to start with? AB. AB, all right. Okay, and I tell you what, let me call this sigma AB max. Why do you think I'm putting another label on it like max? Because it's not the same through and through. It's a very good way of putting it, right? As I twist each one of these segments, it reaches its worst stress on the very outer surface. And as you go inward to the center of the shaft, you have less and less and less and less stress, right? So, you know, one of the ways of looking at that is that the outer surface is doing most of the work, right? It's doing most of the job of carrying these torques. All right? So what formula should I use? Okay. T was way up here, right? TC over J. Okay. So I'll plug in T over in segment AB is just going to be 110 Newton meters. What's C? Yeah, 8 millimeters because it's going to be the diameter over 2. Because when I look at C, C is an outer radius, right? So I'm going to take that 16 millimeters divided by 2. Okay, and if you want, we can turn it into meters. That might make our job a little bit easier after a little while. So if we do that, we could say it is 0.016 meters over 2. All right, now what about J? We're given our dimension of this shaft as a diameter, right? Which means I can just use the version of this that is pi over 32, right? And I can ignore di, right? Because, or I can imagine it being 0, either way. I can basically just leave it off of there because there is no inner diameter. It's not a hollow shaft. So I can just put in here 16, I'll say 0.016 meters raised to the 4th. Okay. Let me plug all this in. So I've got 110 times 0.016 over 2. Down here I've got pi times 0.016 raised to the 4th over 32. Okay, gives me a really big number, but remember that's in pascals because we had all base units. We converted everything to base units. This ends up being newtons per square meter, right? Another way of looking at this is as 136.77 times 10 to the 6th times 10 to the 6th would be the same thing as saying mega, right? So this is 136.77 mega pascals. All right. What about the next segment? Okay. It's kind of similar, mostly similar. Little bit different though, because here, yeah, we've got 70 Newton meters. What's the outer radius? 9 millimeters, right? Let me write that as meters, or in a with a value of meters there, 0.009 meters. Okay. What about J? Yeah, I probably want to use this form right here, right? So pi over 2 times c to the 4th minus b to the 4th. Okay, so what this gives me is 70 times 0.009 divided by pi times, okay, in here I'll do 0.009, oops, not squared, to the 4th minus .007 to the fourth divided by 2. Okay, this gives me 96.4 megapascals. Okay, and then the last one, I'm going to have my maximum stress in segment CD is going to be equal to 60 Newton meters. Do I really care that it's positive or negative? No. Not really. If I'm just, all I'm trying to figure out maybe is how much stress, if I'm trying to compare that against a strength value, I don't really care if it's positive or negative for that, at least for that purpose. All right. Outer radius is 7 millimeters. Here I've got pi over 2 times 7 millimeters to the fourth. And I can ignore any kind of an inner radius because that's a solid piece there as well. So we'll put in here 60 times 0.007 divided by pi times 0.007 raised to the fourth over 2. This gives me 111.36 megapascals. All right. And this is one of the interesting things here, right? That's pretty easy to do those. I just kind of gave you a variety where you either did have an internal radius, right, a hollow shaft, or not, or then you're given one where you have a diameter versus a radius. They don't get that much harder than that, right? You have a few little iterations like that that you could see. But this is one thing, one big takeaway I want you to get from today is that having hollow shafts can be very, very helpful in order to allow you to more efficiently use material. Okay? So the next little segment of the question up there says, which segment is heaviest per unit of length and which is the lightest, assuming uniform material properties? What's a good value we could calculate that will tell us which one is the lightest one per unit of length? Cross-sectional area, right? You might remember, do you remember where we looked at weight? And what was our weight? Rho G A. Well, I didn't tell you what kind of material this is, right? But as long as it's the same kind of material all the way through, the only one of these values that's going to vary is the cross-sectional area. So I can go through and tell you which of these has higher or lower cross-sectional area without too much effort. So for instance, this first one over here, right? What is this area of segment AB? Okay. Well, it's just going to be equal to pi d squared over 4, right? Okay. So pi times the diameter there. I'll just leave them in millimeters, right? For this, at least for this question. 16 squared over 4. Okay. So 201 or so square millimeters. Right? And that's going to be a number that's proportional to how much weight this thing is going to have per unit of length. What about for my next one? Okay. Since these are given in radius values, pi r squared is our formula if we're given it to us, if it's given to us in radius values instead of diameter. So if I just take pi times the outer radius, right, squared minus the inner radius squared, (100.53) square millimeters. And for this last one, the last one is just 7 millimeters right here, right? So 153.9. Square millimeters. So check this out. That segment over on the right end between C and D is about 153% the weight, right, per unit of length as the segment between B and C. It's carrying less torque by a little bit, not a whole lot less, but 60 instead of 70 Newton meters. And look at the stress values, right? This one's carrying more torque and is a significant amount less weight per unit of length than the other one. How does it do that? You're eliminating material that's further to the middle of the member because that's less effective at carrying the torque than the material that's to the outer reaches of the member. Yes. So he said it's just like an I-beam where you're trying to put the area further away from the neutral axis. This is basically the equivalent of that, where we're saying if you can take your cross-sectional area and move it further away from the centroid or the central axis of your torsion members, it's going to be a lot more effective at carrying that load, right? So the heaviest one is the one on the left, where it's a solid 16 millimeter diameter. And look at those, you know, it's got more stress in that with 110 Newton meters carried in it than the one that's half of the weight, right, with 70 Newton meters, right? It's another example of the material to the middle of your shaft is far less effective at carrying the stresses than the material you put more to the outer end. So let me ask you this as our last little thinking question. Are there any limits to that? Like, could I make a member to carry torsion and make it like a 0.5 millimeter thick and, let's say, 12 inches in diameter? Okay. What starts happening at some point? Okay. If you want to do a little experiment, I should have brought one today and I didn't. Take an aluminum can and try twisting it. Because an aluminum can, in theory, should be able to carry quite a bit of torsional load because it is a large diameter, right? But it's really, really thin. So if you take an aluminum can and you start to twist it, another effect actually takes over, and it's an effect that's very similar to the buckling that we saw with respect to columns, right? The material itself doesn't actually stay planar like we expect it to in our derivation here, so it tends to start crumpling it as you turn it before it actually yields the material. Okay, so there is a limit to how far out you can go there, but for right now, just understand it's probably a better idea if you're trying to reduce weight and carry torsion. It's a good idea to have hollow members because the middle material is not as effective as the outer material. Yeah. Yeah, that you can, you know, there are some ways that you can evaluate when kind of that crumpling effect will start happening as opposed to just failing due to excessive stress. But we won't get into that, you know, in here. Yeah. Okay. Or, yeah, so he says on the aluminum can example, if you pull out while you're twisting it, would that help? And the answer is, if you've played with that, it seems like it does help a little bit to pull out while you twist. Okay. What's another one you can try? You can try taking a can that's full, right? It's got internal pressure, and you try twisting that. You might actually find out they can carry a lot more than an empty can when you twist them. So you guys are kind of tapping around an idea here that is going to be big in upcoming classes, and that is when you have combined loading, like not just one of these effects at a time. So the one you first said was basically a combined axial and torsional load, right? The one I mentioned just now is what if it has internal pressure and a torsional load? And we're going to look at some ways that you can deal with multiple effects happening at the same time. But in this class, we're going to keep everything one effect at a time. And I think you guys are probably thankful. I don't know. Some of you, if you search your heart, you might find a little bit of thankfulness in there for not having to deal with more than one effect at a time. Excellent. Well, that's all we've got for today.